So, first one we have here. We have the graph of f of x is below. Find the limit as x approaches 3 of f of x over x squared minus 9. So we've got a top function and we've got a bottom function. And remember, we want to check, is it differentiable around 3? We want to check the limit of the top, limit of the bottom to see if we can use our rule. So, f is differentiable around x equals 3. G is differentiable around x equals 3, since it's a polynomial. Polynomials are differentiable. And the derivative exists at around 3. There are places that it's not differentiable, like over at 2 and over at 4, but around 3, we're differentiable. So we're in good shape there. Now we need to check limit of the top. We need to check limit of the bottom. So starting with limit of the top. As x approaches 3 of f of x, we're going to look at that graph. The limit as x approaches 3 of f of x is 0. Right? As x is getting closer and closer to 3, zooming in on 3, the y coordinates are getting closer and closer to 0. Let's check the limit of the bottom. Limit of the bottom we take 3 and square it. Minus 9. That's 9 minus 9. What do you know? It's 0. So we have our indeterminate form. We have our 0 over 0. So because f and g are differentiable, and our top and our bottom give some indeterminate form, we've got our two things. We would write L'Hopital's rule can be used if I had more room on this square. But I need to actually do the limit. So limit as x approaches 3 of f of x over x squared minus 9. And L'Hopital's rule says that this is the same as the limit of derivative of top over derivative of bottom. Remember, this is different from the quotient rule. It's not low d high minus high d low squared what's below. It is just take derivative of the top, take derivative of the bottom. So derivative of f is f prime. Wow, that was hard. Derivative of x squared minus 9 is 2x. Now let's see if we can plug in 3. F prime of 3, that means that we are tracking our slope at 3, right? That's f prime is our derivative, is our slope. So f prime at 3, let's see, we're going down 2 and to the right 1, so that's negative 2. And then 2 times 3 is 6, so negative 1/3 is our limit. So that's a way that our kind of function form of doing this is combined with looking at a graph. Looking at a graph to determine our limit, and not just our limit of the function, but we also had to figure out the limit of the derivative by reasoning out what our slope was at those points. All right, let's try the one on the bottom right. One on the bottom right is a hard one, and that's going to be the case on the next page too, because it's combining multiple different ideas. To get f of x, we're going to have to do separation of variables. It's not a hard separation of variables, but it is a separation of variables. We're going to separate out the variables. We need to multiply by the y to get it over here. We need to multiply the dx to get it over here. And so when I take the antiderivative, I'll see. I'm going to go ahead and simplify this a little bit. I'm going to multiply all this by 2. Two times a number is still a number, so I still have a constant there. I'll go ahead and solve for c here. F of 0 is 3. C is 9. Which means that y is the positive square root. I know it's a positive square root because I want the output to be positive. Again, you could have solved for all the way down for y and then plugged in and solved for c. It's just wherever you find it easiest to solve for c. Top and bottom are both going to be differentiable. I'll keep the y equals down here. And we'll find limit of the top, limit of the bottom. F of 0, 0 squared plus 9, all under square root, and a minus 3. That's the square root of minus 3. Minus 3 is 0. How about that? No one saw it coming. Now let's see what the limit of the bottom is. Limit of the bottom. Oh, that's going to be e to the 0 minus 1. E to the 0 is 1 minus 1 is 0. There we have it. And we have 0 over 0. We have them both differentiable, so we can use Hopital's rule. Of f of x minus 3 over e to the x squared minus 1. Derivative e to the x squared is e to the x squared. But then we need a chain rule. Times derivative of the inside part. Derivative of x squared is 2x. Right, the function's inside of another function because we have that x squared up in the exponent. So now, What is f prime of x? Sorry, limit. Oh, it's the dy dx up here. That was our derivative. So it was x over y. Over sorry, e to the x squared times 2x. And this is where it becomes even more difficult because this is still 0 over 0. X over, we have y times 2x times e to the x squared. Plug in top, I get 0. Plug in bottom, I get 0. But on some problems, that's going to mean that you would see if you can use Hopital's rule again. But in this case, what we have is we have a common factor here. We have a common factor of these x's here that we can cancel. Which means, we're almost done. This is 1 over 2y e to the x squared. So we're canceling that common factor of x, and now we can plug in 0. When x was 0, what was y? What should we put in for y? It should be 3. E to the 0 squared. E to the 0 is going to be 1, so it's going to be 1 over 6. Whew, that was a lot. So, separation of variables happened. Then we did our L'Hopital's rule. Then we got our factor to cancel there. And that gave us our process.